alternate to reject the image frequency is an image rejection mixer. You can see in this circuit, it employs two multipliers. Okay, so they're ordinary multipliers, and you see over here, this is the local oscillator frequency, and you are for the upper multiplier. Let's call this the upper multiplier. This is upper multiplier, and this is the down, the lower multiplier. So this is the lower multiplier. For the upper multiplier, there's a 90-degree delay, and therefore, if for example this is cosine, okay, so you have a cosine at the lower multiplier, and due to this 90-degree delay shift, you produce a sine over here. Okay, so the circuit uses two ordinary mixers, multipliers, which you can see over here. The input is the RF, okay, and if you recall the local oscillator frequency, what we were discussing before and what we have seen before in the super heterodyne receivers, that's equal to your the input FRF plus the intermediate frequency. Okay, now FRF could be higher or lower than the intermediate frequency, but anyways, for a standard AM broadcast, this FIF is standardized at 455 kilohertz. So once you mix this RF FRF with the local oscillator frequency, the difference is FIF, okay, which goes inside the IF bandpass filter, and then it goes to an appropriate amplification, RF amplification for proper detection before the detector. So what happens over here is that you have these two multipliers. So one is 90-degree delay, so one is sine, the other is cosine over here. So the upper multiplier has a 90-degree delay in its connection to the local oscillator, so it forms the product with sine omega LOT. So this is sine omega LOT, okay, and the lower multiplier, you see, it forms the product of cosine omega LOT. Product with what? Product with an input signal, that is omega LO plus minus omega IF, right? I mean, you can write this. This is again omega RF. If you see this, that's your input, because RF can be written as LO minus IF, right? LO minus IF, and it could be plus or minus depending on whether the input signal is above or below the local oscillator frequency. Okay. Similarly, the upper multiplier, which was 90-degree delay in connection to the local oscillator, formed the product with sine omega LOT and cosine LO plus minus omega IF. Okay. So now once this multiplication happens, you're going to have new frequencies which are expected. So for the upper multiplier, which is having sine omega LO. Okay, so this is sine omega LO. Let me put it down over here. This sine omega LO t, right? The output over here will consist of the sum and difference of these frequencies. This, the frequency over here, and the frequency over here, that is omega LO. Okay, so you see at these two terms, this is sine omega LO, this is cosine omega LO. So the sum will be at 2 omega LO plus minus omega IF, or you will have a term that is simply omega IF. Okay, only one frequency, omega IF, you consider difference. So if you neglect the sum frequency terms, the output of the upper and lower multipliers respectively is sine minus plus sine omega IF. This is for the upper mixer, and this is for the lower mixer. Okay, if you can derive this from the trigonometric identity. So over here you have the product of sine A, cosine B. Then over here you have again cosine A, cosine B. So this is your lower multiplier, and the product of the lower multiplier is this. Okay, is this. And if you're neglecting the sum frequencies, okay, we don't need the sum frequency, because we're going to process the signal before demodulation at the IF stage, so we need the frequency at the intermediate. And for the upper multiplier, this is what you get over here. Okay, now if you look at this convention minus plus, it means if you're considering the plus sign, Okay, if the frequency is, let's say the frequency is omega LO plus omega IF. So if you are considering the frequency that is higher than the local oscillator frequency, then this is minus. Okay, and similarly, if you're considering minus, which is, I mean, the frequency that is lower than the local oscillator frequency, then this is plus. Okay, so for minus, this is plus over here. Okay, so you can see the sign convention. Now the output from the lower multiplier is delayed by 90 degrees. So over here, see the output over here of the lower multiplier is delayed by 90 degree, and this is going to produce, if this is so now what happens is that you have both sine terms. Okay, for example, over here there was a cosine. Now you will have a sine over here. So the upper and lower side, lower signals at the input and adder is again minus plus sine omega IFT and sine omega IFT. So both have the same frequencies. Now depending on whether the frequency that you considered at the input, whether the frequency was higher than the intermediate frequency or lower than the intermediate frequency, you will have the sum. Okay, you will have the sum of the two inputs before the adder. You will have the sum equal to IF. If you consider the difference, if you consider the frequency, intermediate frequency, which is lower than the local oscillator frequency. So in this case, so this is the case where FRF is equals to LO. FLO, if you write this in hertz, this is FLO minus FIF. Okay, so in this case, the output is going to be the intermediate frequency. Okay, why is that? Because you see, if you consider the negative term over here, and that's positive. Okay, so positive plus positive, which is delayed by 90 degrees. This is because you know that the lower mixer is delayed by 90 degrees over here. This is again sine. So you have the sine term over here. Actually, this term is like this. So if you consider the positive sign, you consider this positive sign over here, then you have the output that is twice sine omega IFT. But if you are considering the frequency that is higher than the local oscillator plus with a minus, if the frequency is higher than the local oscillator frequency, then a minus sign comes up over here. Okay, and the addition is going to produce the result that is equal to 0. And this result is for if your RF was equal to FLO plus FIF. Okay, so if you're considering the frequencies above the local oscillator frequency, okay, so if that was the case, well, then your output is 0. Okay, so basically what we are doing is you are tracking the frequencies which are below the local oscillator. Okay, you are not interested in the frequencies above the local oscillator. Okay, for that you get a result that is 0. Okay, so we don't need high frequencies. This is like a band pass filter again. So we need the frequency at the output that is intermediate. Okay, so but when the frequency is omega LO plus omega IF over here, the output of the adder is 0. So what it means is that this mixer rejects the signal above the local oscillator frequency. So in practice, this circuit might provide 20 to 40 decibels of image rejection. Okay, because the images, you know, images again, the higher frequency images is higher, so it's twice IF, whatever the intermediate frequency is, plus the FRF. So if this frequency, of course, is greater than your local oscillator frequency, okay, if this frequency becomes greater than the local oscillator frequency, FLO, which otherwise is set to FRF, which is equal to FRF plus FI, which is not the image, the intermediate frequency. Okay, you can see that this frequency is greater than the local oscillator frequency, which otherwise commonly is FRF plus FIF. This image rejection is going to provide attenuation to such signals. Okay, so this mixer basically rejects the signals above the local oscillator frequency, including the image rejection. So it might provide 20 to 40 dBs of image rejection as well. We don't need the higher frequencies. Okay, we don't need them. So it can be used together with a standard filtering techniques to provide further rejection. Okay, so it's a very useful circuit to provide image rejection, as well as we don't need frequencies, okay, which are greater than the local oscillator frequencies. So that's what the circuit does.